Okay, so last time I introduced the idea of two elimination reactions. The first one was to start with an amine and to react it with 3 equivalents of an alkyl iodide or an alkyl chloride or bromide in basic conditions, so that once the amine undergoes the SN2 reaction with the methyl halide, we end up forming the ammonium ion, and then the base will pull it off so that it can become a nucleophile again. So what that does is that adds then 3 methyl groups to the nitrogen, making it a plus charge and setting up for the elimination reaction. So now that N plus is a good leaving group, so that when I apply nothing more than heat, I've got my leaving group on the alpha carbon, and then I have, in this case, 2 beta carbons, each of which has at least 1 beta hydrogen, so that when I heat this mixture, I'm going to lose the ammonium as the leaving group, and I'm also going to lose a beta H+. And the question was, which beta H+ am I going to lose? I'm going to lose the hydrogen that's attached to the least substituted carbon, so that I'm going to make the Hofmann product or the least stable product. So this reaction is totally based on the number of beta hydrogens. So the carbon with the most beta hydrogens is going to be the one that loses the beta hydrogen to form the product. And so by definition then, Hofmann elimination, which is what this is, will always give the least substituted double bond. So in this case, I'm going to lose an H+ and the ammonium at the same time, so that I'm going to form that as my major product. And so this rule in terms of basically the carbon with the most beta hydrogens is going to become the major product. I could restate that a little bit by saying that this reaction is based on, the major product is based on the hydrogen becoming anti-periplanar to the leaving group. And the more hydrogens and the easier that is, that's going to lead to the major product. So in this case, I've got 3 beta hydrogens, any of which could become anti-periplanar to the nitrogen, so that's an easier or more conformations that lead to the product than over here, where there's just a single hydrogen that has to become anti-periplanar, and that conformation may not be the most stable conformation of that molecule. So we changed the rules in Hofmann. So it's not about more stable product, it's more or less about the sort of transition state energy, but there's no base to remove it, so we don't take that into account. Okay? So that's the total, that's the rule is, for Hofmann, we're going to get the product that comes from the carbon with the most beta hydrogens. Okay? So that was Hofmann. And the reaction has to go through an anti-periplanar geometry. Now, at the end of class, we were looking at the other reaction. The other reaction would be to take that amine, that same amine with an NH2, and first of all only react it with 2 equivalents of a methyl halide, again under basic conditions, so that I could put two methyl groups on the nitrogen. And then I'm going to treat that dimethylamine with a mild oxidizer. And the mild oxidizer could be something like hydrogen peroxide, or another one that's commonly used is a peroxy acid. And so when I do that, what I'm going to end up doing is I'm going to end up having the 2 methyl groups, but now, I have to write this the right way. So I've got 2 methyl groups, and then what that ends up doing is forming this species, which is called an amine oxide. So that peroxy acid or hydrogen peroxide reacts with the nitrogen, and it forms this amine oxide where the nitrogen has a plus charge and the oxygen has a negative charge. Now, this is what's called Cope elimination. And Hoffman and Cope eliminations both give the least substituted product as the major product. Where they differ is whether the reaction, well, they differ in the mechanisms, but they also differ in terms of whether the reaction goes by anti-periplanar geometry or by a periplanar geometry. So in this Cope elimination, what's going to happen is, and I'm going to rewrite this on the other side, I'm going to rewrite it over here, that when I have my amine oxide, and now I have my, again, alpha, beta, and then on the other side, the other beta carbon, this O minus is going to come down and it's going to grab one of the least substituted beta hydrogen. This pair of electrons moves here, and then that pair of electrons moves into the N plus. So this is a 5-member transition state. And with the 5-member transition states, remember there's not enough space for, if for instance this was a ring, I could only remove a hydrogen that's on the same side as the nitrogen. So the nitrogen doesn't have the ability, the oxygen doesn't have the ability to stretch very far. But the critical part is this is now periplanar. And so when that transition state occurs, that 5-member transition state, on the other side, what I'm going to end up with is I'm going to end up with a double bond to the least substituted carbon, and then I'm going to end up with as my nitrogen product what's called a hydroxylamine. So same final product in terms of both of these form the amine, or form the double bond that is the least substituted. Both of these reactions remove the hydrogen that is the hydrogens that are most sterically accessible, except that's not really the best way to say it because there's no base that's removing this. This is all done with heat. Okay, so that's Cope and Hoffman elimination. And again, where they differ is Hoffman is anti-periplanar and Cope is periplanar. Is everybody kind of with me? That's where we end. That's where we ended on Wednesday. So then let's make it interesting then. So I can, let me think of a molecule here. So now let's put some stereochemistry in. And I'm going to go both ways. I'm going to add 3-methyl iodides under basic conditions. I'm just going to abbreviate the ethyl group as ethyl, and then hydrogen, methyl. So the first step is I'm going to alkylate this nitrogen with 3 methyl groups. So that's my molecule that's going to undergo Hoffman elimination. Or I could go on this side. I could add 2 methyl groups. And then a peroxy acid. So that on this side I'm going to have my nitrogen as my dimethyl, as my amine oxide, and then so I'm going to set that molecule up for both Cope on the left and Hoffman on the right. Now, for both of these reactions, I would ask you to write, I could ask it one of 2 ways. I could say write the major and the minor product of these 2 reactions, or if it was in a multiple choice format, I would give you all the possible products and say which one of these is the major product, or I might say write all of the possible products. So going back to basics, this is an elimination. So that means here's my alpha carbon, here's my beta carbon, and here's my beta carbon on the other side. Over here's my alpha carbon, my beta carbon, and my beta carbon on the other side. Do those have hydrogens? Yes. I've got 3 hydrogens, 3 beta hydrogens attached to the methyl group, and I've got 1 beta hydrogen attached to the other beta carbon on the other side. I'm going to label those A and B, A and B. And so my question is this. What's going to be the major product? Which hydrogen is going to be removed to form the major product? The ones that I labeled A or the ones that I labeled B? Okay. So if you got your cards, if you need a card, although my suspicion is that this card will override another card that's already out, but at least you're playing along. So which Okay, so which one is it? Is it A? Am I going to remove A or B to form the major product? Okay, let's see what we got. 22 A's. Correct. I'm going to remove the hydrogen that forms the least stable alkene. It's not mine. And if it's your wake up alarm, it's a little late. So we're going to form the double bond then. So when I do this reaction with heat, the major product of this reaction is going to be that product. Right? This is going to be the major product. For both reactions. So that's going to be the major product for both reactions, and that's the Zaitsev and that's the Cope major products, the ones that are least substituted. But I'm more interested in the second product that's going to be formed. I'm more interested in what happens if we lose beta hydrogen B. How that product's going to look. So for the ammonium salt, which is Hoffman elimination, we know we're going to get a double bond to the beta carbon on the left, and I'm going to have 4 things attached to that. On the right-hand side, it's going to be a hydrogen and a methyl. And on the left-hand side, after eliminating the beta hydrogen, it's going to be an ethyl and a methyl. So my question is, for Hoffman elimination, will the methyls be cis or will the methyls be trans in that product? And for the Hoffman, or for the Cope elimination, same thing. I'm going to end up with a double bond like that. I'm going to end up with the methyl hydrogen on the right-hand side and the methyl in the ethyl group on the left-hand side. After Cope elimination, will the methyl groups be cis or will they be trans? So, let's work on Hoffman first. So I'll give you a minute or two. Write the product that you get by the loss of this beta hydrogen in Hoffman elimination. You can discuss if you want. Give you 3 minutes and then we'll vote. Are we ready to vote? Okay. So let's vote. What are we voting on? Right. So there's on the right side there's going to be a hydrogen and a methyl. And then on the left-hand side, there's going to be an ethyl and a methyl. So the question is, are those two methyls cis, or are they trans? And those are your only two choices. I guess your other choice could be, don't know. If you want to be honest and say, I don't have any idea what's going on. This is for Hoffman elimination. This is for Hoffman. So this is for the ammonium. Okay, so let's go ahead and vote. All right. Well, one person doesn't know, but it's 11-12. It's 11 A's and 12 B's, which is normally the way it works with this the first time through. It's usually a 50-50 split, and I have a feeling if we discuss for a minute, it's going to either come back split again or with more don't knows. So what do I have to do? Hoffman, the nitrogen, the N plus, and the beta hydrogen have to be in what positions? For Hoffman, they have to be anti-periplanar. So that means in this sawhorse projection, I've got to put that geometry basically like that, where my N plus 3CH3 group ammonium and the beta hydrogen are going to have to be anti-periplanar to each other. So dealing with the right-hand carbon, that means that nitrogen is coming out of the board, so I just got to move it back a little bit to put it in the plane. And that's not really, if I do that, if I move that back, the methyl group is going to come forward and the hydrogen's going to be back. So all I do is make a 30-degree rotation to get it planar. And then for the hydrogen, what do I have to do? And, let's start with the easier way of doing this. That wasn't necessarily the easier way. If you're looking at it going, oh, that wasn't too bad, okay, then you win. But let's keep it in this conformation. All right. So in order for this nitrogen, I want to put the beta hydrogen and the nitrogen here in the pre-existing Newman. Okay. So I want to rotate the nitrogen down so I'm going to rotate the nitrogen down here so it's in the plane. And then what's going to happen to the methyl group? It's going to rotate back, and then what's going to happen with the hydrogen? It's going to rotate up. So first thing is put the nitrogen into the planar positions, the positions that are in the plane of the screen. Now I got to put the beta hydrogen into this upper position, so I'm going to go ahead and rotate it up. That means the ethyl group is going to come down, and this methyl group is going to come over here. So in my existing Newman projection, I want to make the beta hydrogen and the nitrogen leaving group anti-periplanar, which I've just done. And so now that hydrogen's going to go there, and the nitrogen is going to leave. The two positions that are bold are going to be cis to each other. So that's the hydrogen and the ethyl group. And the two positions that are on dashed wedges, the methyl and the other methyl, are also going to be cis to each other. So the correct answer is that the two methyl groups are going to be cis. Does that make sense? I mean, I could just rotate things up. If you don't like this, you could put this molecule into a Newman projection, because as I'm looking at this molecule, basically I'm looking at a Newman projection like this, and I want the hydrogen and the N+ species to be anti-periplanar. So you could do this in a Newman projection if you wanted to, but in a sawhorse, just make those two on the in-plane positions. And then the two bolds are cis and the two dashed are cis. All right, I'm not hearing any objections. So, what about cope? What about the cope? So in the cope, let me draw it out exactly the same way, only in this case, now on the bold wedge, I'm going to have my nitrogen with my two methyls and my O-. I'm going to have my methyl group and my hydrogen, and over here I'm going to have my ethyl group, my hydrogen, and my methyl group. And now, again, if I'm going to remove that hydrogen, I now have to put that beta hydrogen to this amine oxide. What's the geometry for cope? It's going to be periplanar. So what does that mean? That means I have to put this molecule into this kind of sawhorse geometry. So notice on the left-hand side, nothing changed. On the right-hand side, I'm now going to take that nitrogen, which is pointing towards you, and I'm going to move it back so it's in the plane. So I'm just going to slide this a little bit back so that the N plus O- is now in the plane. What does that mean? As I move the nitrogen back, what happens to the methyl group? It comes forward, and the hydrogen is still in the back. And then over here I've got an ethyl I've got a hydrogen, and I've got a methyl. So I have to just move one of the groups back a little bit. Okay, so now I'm still not in the right conformation, right? I've got to move this hydrogen up here, move this ethyl group down here, and move that methyl group into the back so that I can put it in the proper periplanar geometry. So now I've got my nitrogen with my O-, my hydrogen and my methyl group, so the right-hand carbon stays the same. The left-hand carbon, the hydrogen goes up here, the ethyl group comes down here, and the methyl group goes into the back. So now my amine oxide can grab the hydrogen, that pair of electrons can move like that, and then that pair of electrons can go to the nitrogen. And so again, now in this case, the groups that are bold are going to be cis, the groups that are trans are going to be cis, so I'm going to end up with a double bond. So I'm going to end up with my ethyl group and my methyl group being cis, and my hydrogen and my methyl group being cis, so that in this case, in cope elimination, the two methyl groups are now trans to each other. Which, coming from the same molecule, one the methyl groups would have been cis, and then the other one the methyl groups would have been trans. Which is which? That's why you have to write out the intermediates. So if you're, if you're kind of like, hey, haven't we done this before? Yeah. I think we've done it multiple times before, but we did it with E2 eliminations because that's basically what this is an E2 elimination, except I'm not using a base. So this is the trickiest part of Hoffman and cope elimination. And notice it wasn't even writing the major product. The major product's easy. Because normally for these systems, there's no stereochemistry to form the major product, because the major product had 3 hydrogens. It was a primary carbon with no stereochemistry. The tricky part is writing the next product. And if you begin to look at an older exam, you'll see that, I think, as well as I think I have a whole multiple choice set of problems that I usually give out in class that I will either put online or I'll give them out in class again. But usually when I ask this question, I ask what's the major product and then what's the other possible product. So it's the other possible product is where we have control now with Hoffman and with cope. I can now form whichever stereoisomer I want. I want the 2 methyl groups cis, Hoffman. I want the 2 methyl groups trans. In this case, I would use cope. And so, I can write these problems all day, and I can change them a little bit. So, is this the case for this reaction? Yes. Could I change this product and make it exactly the opposite? Yes. So you got to take them case by case. But the major product always had the double bond to that methyl group. But it's the second product that's the one that's trickier. So I think you have to do this for finishing up the chapter 24, whatever chapter we're on, in Top Hat, those problems for Monday that are due. The remainder of this chapter is diazonium salts. We did diazonium salts. Hopefully you haven't forgot about diazonium salts, but that's what the remainder of the chapter is. So I'll leave that to you. Right. So in amines, this is the trickiest part, because we're now we have to go back and think about sawhorses. Right. So that's going to end that chapter. Let's see. Wait. The stuff that's due Monday isn't this chapter. Right, it's the last chapter, isn't it? So technically we have now finished this chapter, which means 2 lecture periods would put us at Wednesday. This chapter's problems are going to be due the Wednesday when we get back. And remember, when we get back, we have class on Tuesday and Wednesday, because Tuesday's not a real Tuesday. Tuesday's a Monday, Wednesday, or Friday. I think it's a Monday. But next week, Monday, Tuesday, and Wednesday are real. They're real Monday, Tuesday, Wednesday. Then when we get back, it's Monday, Wednesday, and then Thursday, Friday. And since no one else, so I get asked this question, I'll take a second. Why do we do this? That's a good question. I've been here now 25 years. I got my 25-year watch, which was okay. And got to meet the president for the first time. Exchange words. Congratulations. Thank you. But why do we do this? Because nobody else does this. The reason we do this is because we have to have an equal number of Monday, Tuesday, Wednesday, Thursdays, and Fridays. Because if we have a single class that meets on a Monday, if we miss a Monday, it's like missing a week's worth of classes. And there are like federal guidelines that say you have to meet so many weeks out of the semester. So that's why we do this. I don't know what other schools do, but they apparently don't do what we do. So that's why we have these weird phantom days on our schedule. And we have always had them as long as I've been here. Okay. Let me set up for the next chapter, because we are now, like, I think 3 chapters away from the end, which is not the number of weeks left, so we'll have to kind of pick up the pace a little bit, but that's my problem, not yours. Well, it'll become yours. So the next chapter is carboxylic acids. And then after that, it's carboxylic acid derivatives. So carboxylic acids. We actually know a lot of reactions of carboxylic acids. We know how to make them. We know a lot of different methods to make them. That's going to be the first part of the chapter, is reviewing those. And then the reactions of carboxylic acids are going to be what's next, and we do know some of those. Okay. So in this case, what we're going to talk about is sort of the mechanism of reacting carboxylic acids. And one of the reactions we do know is that we can do this reaction with H+, because we just finished that up in lab. And so if we think about writing the mechanisms of carboxylic acids with amines, or with alcohols, in this case, we're going to use a combination of the mechanism that we used for an aldehyde, for aldehydes and ketones. But we now have the problem that that group can leave. So when we start looking at carboxylic acids and their derivatives, and I'm going to kind of mix them all together here, I'm now going to look at a carbonyl group where the Y group can leave. With aldehydes and ketones, when that Y group was a carbon and a hydrogen group, it couldn't leave. But now it can. So that's going to lead to basically substituting my nucleophile for my Y group. So if I take a nucleophile and it comes in and it adds to the carbonyl, if it adds to the carbonyl, when I try and bring my O- back down, either the nucleophile will leave, which means I go backwards, or now the Y group is going to leave, which means I'm going to end up substituting that Y group now with the nucleophile. So that when the O- comes back down, something's got to leave, either the nucleophile or the Y group. If the Y group leads, I end up with substitution products. So what I'm going to do on Monday is I'm going to kind of lay out both the carboxylic acids and the derivatives case, because I'm going to need to know which one of those two groups is a better nucleophile. And that's going to tell me whether the reaction really doesn't go or whether or not I'm going to do substitution. Okay. All right, you can turn your homework problems in. I will hopefully have all that stuff graded for Monday. I will update the web, including putting some deadlines on Top Hat. And if you have any questions, by all means, come and ask by email or come and see me.